All right, so we're going to talk about section 4.3 today. Double integrals in polar coordinates. So just a couple of reminders for polar coordinates. X equals r cosine theta. Y equals r sine theta. These are just some substitutions that we're going to need as we do these integrals. X squared plus y squared equals r squared. And tangent theta equals y over x. So we'll need these as we do some of these integrals. So what we're going to do is, when we did double integrals in rectangular coordinates, we divided our region into rectangular, little small rectangles. So for polar coordinates, we're going to divide our region in the xy plane into polar sectors. So we'll draw a sketch of what we're talking about here. And in our polar coordinates, this is theta equals pi over 2. So theta equals 0 on this axis. And we're dividing our region into little sectors. And polar sectors look something like this. And we're going from theta equals alpha to up here theta equals beta. And this is our region. And we're going to look at one small sector in here. And in this sector, we have the coordinates here, r sub I and theta sub I. So we're dividing our sector into a bunch of small pieces. So the coordinates of that point in that sector are r sub I, theta sub I. And this little distance here is delta r sub I. So that's our small change in radius for this small sector. So let's look at just one. We're just going to look at one of these sectors to develop our formula for our double integral in polar coordinates. So we're just going to look at this one sector. So we'll redraw that. So if our axes are here, we're just interested in one of these. So this distance here is delta theta. And this distance here is delta r. And we're going from r equals a to r equals b for this little sector. And this is the region that we're interested in here. So we're looking at this little region as a polar rectangle. Now the area of a circular sector with our radius r and a central angle theta is area equals 1/2 r squared theta. So that's the area of a circular sector. The area of this region, area of this small region, is our area is 1/2 b squared delta theta minus 1/2 a squared delta theta. So we're just finding the area of the small region. I can rewrite this as that equals 1/2 b squared minus a squared delta theta. Or I'm going to factor this 1/2 a plus b times b minus a delta theta. So I just factored this. And I'm going to write this as r delta theta, where this r is the average radius. So this r is the average radius of our sector. And if we're finding the volume, if we're interested in the volume bounded by this region in the xy plane underneath some surface, then we're looking at the volume like we did with rectangular coordinates, the volume of a rectangular prism, where this little sector is our base. So our volume of one prism in the region under f of xy in our region is f of xy times delta a sub I, where delta a sub I is just the area of that little region. And for what we have here in our region is f of xy. And this is, we'll call it our ith region, or our ith little interval. X sub I, y sub I, times the average radius, times delta r, times delta theta. So that's the area of one of our little rectangles. And because we're expressing everything in terms of r and theta, I'm going to write f in terms of r and theta. So our volume equals some function. X is r sub I cosine theta sub I, and y is r sub I sine theta sub I, times the average radius times delta r delta theta. So that's a volume of one of our small rectangular prisms in that region. If we take the size of our polar area, we take the size of this little region and we make it smaller and smaller and smaller, so delta r gets smaller and delta theta gets smaller. The average radius becomes the radius of that small sector. So our average radius is the radius of that tiny, tiny, tiny little sector. And we sum all of these. The volume fits with our definition of a double integral. So the volume underneath our surface f of xy in the region becomes the sum of all of these tiny prisms, the volume of all these tiny prisms, and we sum that over our region. So we say that this fits in with our definition of our double integral over a region, f of xy dA, and for our purposes here, that is the sum, and we're approximating here, we're not taking the limit yet, approximately equal to I equals 1 to k over our region, f of r sub I cosine theta sub I, r sub I sine theta sub I, r delta theta, and then as we take the limit, as our delta r and our delta theta become smaller and smaller, we get our double integral for the volume under that surface over the region. I'm going to write the double integral of f of xy dA equals the double integral, I'm going to say over S of f of r sub I cosine theta sub I, r sub I sine theta sub I, r dr d theta. This r dr d theta is our differential of area in polar coordinates. If we're doing a double integral in polar coordinates, this whole thing is dA. That will always be in as part of our double integral in polar coordinates. The r dr d theta is our dA in polar coordinates. And this shouldn't be r, this should be an f. This is my function. So we express our function in terms of r and theta, depending on what it is, and this should be a cosine theta. So we express our function in terms of r and theta, and our area, our little increment, our differential of area is r dr d theta. This reminds me of there was a Simpsons episode once where Lisa went to a gifted and talented school, and all the kids in the elementary school were doing integrals, and they started laughing, and Lisa didn't get the joke, but the teacher had to explain in the integrand they ended up with r dr dr. And the reason I wrote this S here instead of the R is just to remind us that we're in a different coordinate system. That reminds us we're in polar coordinates rather than rectangular coordinates. So we have to look at our limits differently, and our area, our differential of area is different in polar coordinates. Now, when we defined our double integral in rectangular coordinates, we said that this tells us what the double integral is. It doesn't tell us how to evaluate it. We evaluate it very similar to the way that we evaluated double integrals in rectangular coordinates. Fubini, it's similar to Fubini's theorem. We can divide our region in two different ways and evaluate these as iterated integrals. So let's write down how we evaluate these. So we have two different possibilities. We have one region that we call radially simple, or our book calls it R simple. And in that case, we have our our region looks something like this. And we have some functions of theta. R is defined as some function of theta. This is R equals g2 of theta, and this is r equals g1 of theta. We call this r simple or radially simple. And for this, we set our representative rectangles this way. And to evaluate this, to evaluate a double integral over a region like this, and we're saying theta goes from alpha to beta. So our double integral of s of f of xy dA in this case equals the double integral from alpha to beta of the integral of g1 of theta to g2 of theta f of r theta, r d theta. So we express our function in terms of r and theta, and this is our area differential. Our other region is called angularly simple, and I think our book calls it asimple, maybe. And for those regions, we're going to have something like this. And this is, theta is some function of the radius. And the radius goes from A to B. And in this case, we just switch our order of integration around, and our double integral over our region equals the integral of the radius goes from A to B of g1 of theta, g2 of theta as our limits, sorry, h, thank you. F of r theta, r d theta dr.
Shouldn't it be h of r?
Yes, it should be h of r. Our angle is a function of the radius. Thank you. So just like we would expect, in this we set our representative rectangle, our polar rectangle, I guess we'd call it, this way. And our little section here is r d theta. And we call this angularly simple. Yes?
How do we get rid of the r?
Well, here when we have our function of r and theta, it will get combined with our function.
So you're just multiplying that out.
It's just a multiplying factor. So it'll end up being something that's part of our integrand. But it's always we always have to include it in our double integrals for polar coordinates. This is our dA, r d theta, r d theta dr, one of the two. When we look at a couple of examples, it'll make a little more sense. And my preference with double integrals and polar coordinates, I like to set in rectangular coordinates. I like to set my rectangles vertically. I usually like to try to do double integrals and polar coordinates in this order, r d theta, if possible. and it's just a personal preference. All right, so let's take a look at a couple of examples. Any other questions? Let's look at a really easy one first. So we want to evaluate, we want to find we're going to evaluate this double integral, 0 to pi over 4, 0 to 4, r squared. Actually, let me do this. Our function, I'm going to go backwards here. I got ahead of myself. So my function is r sine theta cosine theta. And my region is zero less than or equal to theta less than or equal to pi over 4, and 0 less than or equal to r less than or equal to 4. So this is my function. I want to find the volume under this function on this region. So if I sketch my region really quickly, 0 to pi over 4 in terms of polar coordinates, where does that take me? Halfway. So this is theta equals pi over 4. And r equals 4. That's just a circle radius 4. So here's my region. So my integral, my volume, is going to be the integral of theta equals 0 to 4, r equals 0 to 4, I'm sorry, theta equals 0 to pi over 4, r equals 0 to 4 of r sine theta cosine theta, r dr d theta, and I can rewrite that. That's the integral of 0 to pi over 4, 0 to 4 of r squared sine theta cosine theta dr d theta. And when I evaluate this, my first integral is of dr, so I just end up with r cubed over 3 evaluated on 0 to 4. And my second integral is going to be the integral of sine theta cosine theta d theta, another easy one to evaluate. So this turns out to be a very easy integral to evaluate in polar coordinates. If I evaluate that out, I end up with 16/3. So this r just gets combined with whatever my function is inside the integrand. Questions? U is sine theta, du is cosine theta, so you end up with sine squared theta over 2. Nice easy one. All right, let's look at another one. Do we have any questions on that one before we go on? So let's look at the integral. I want to start with the integral, and we're going to sketch the region. 0 to a, 0 to square root of a squared minus x squared, x dy dx. So we want to evaluate this integral. Now, if I were to evaluate this, I end up with xy, and when I put my limits in, I end up with square root of a squared minus x squared So I have x, y. So I have, anyway, I end up with this in my integrand. So let's see if this is easier in polar coordinates. So let's sketch the region. So our limits tell us that y equals 0 to y equals square root of a squared minus x squared. And x equals 0 to x equals a. So my region, like so. Y equals square root of a squared minus x squared. What kind of shape is that? That's a circle. And x goes from 0 to a. So x goes from here, x equals a. So if I change this to polar coordinates, this is my region. So I change this to polar coordinates, I get the volume, my integral, equals the integral of r equals 0 to what? A, and theta equals 0 to pi halves. So I'm going to say 0 to pi over 2, 0 to a, and x is r cosine theta, r dr d theta. And when I evaluate this, I get the integral from 0 to pi over 2 of r squared over 2 cosine theta evaluated on, whoops, r cubed over 3, thank you. R cubed over 3, because I have an r squared there, evaluated on 0 to a d theta. So I just end up with integral 0 to pi over 2 of a cubed over 3 cosine theta d theta, which is another easy integral to evaluate. So this when depending on our region, switching to polar coordinates can make our life much easier. Questions on that one? Let me pick out another example here. We want the solid, we want the volume of the solid bounded by z equals x squared plus y squared plus 3. Z equals 0 and x squared plus y squared equals 1. So these two, the last two conditions give us our region. The region that we're interested in is bounded by z equals 0. So it's between this surface and the xy plane. Z equals 0 is the xy plane. And in the xy plane, this is the boundary of my region. So my region in the xy plane is just this circle, x squared plus y squared equals 1. And x squared plus y squared equals 1 is the entire circle. This is just a quarter of my region. So I'm going to call this r divided by 4. So our volume is going to be the double integral over this region, over the circle of this, underneath this surface. So we need to express z in terms of r and theta. So how are we going to express z in terms of r and theta? Z equals r squared plus 3. So what we're integrating, our volume is going to be 4 times the integral, and we're just looking at this region because our integral is symmetrical. So theta goes from 0 to pi over 2. R equals 0 to 1 of r squared plus 3 r dr d theta. And this one is a very, very easy integral to evaluate. When we evaluate it out, we should end up with 7 pi over 2. So we just end up with r cubed plus 3r dr, evaluated on 0 to 1. And then for a theta integral, we just have a d theta. Questions on that? All right, I'm going to stop for now. Homework. Page 1006. Yep, we made it into the thousands. There you go.